Hello, everybody. Is the live working? Look at that. I gave myself a plum disc. Or not plum disc, plum dusk. Back to normal. Okay. I think the live is living. Here's the light on. Okay, perfect. I'm gonna go get my beverage. You should grab one too while we wait for people to join and then start with our live tonight. Okay, here is this. We're gonna be referencing this tonight for sure. For sure. Therefore, here it is. Oh, hello. Thank you for liking the live. How are you doing, my darlings? How are you doing? Hi, Bougie baby. I just got back from my swim. So hopefully you are prepared for another Zabardast live studying cosmology. Tonight we will do cosmology. Of course, why not? Of course, and why not? Say hi in the chat if you can. And please do like and subscribe. Getting my live pulled up on the monitor here. Okay, I'll be right back. Woody. Hi, Woody. Hi, Woody, baby. What, did you not get any snacks? Mama will give you. Hi guys, thank you so much for joining. Please do like and subscribe, and we will be talking about dark energy tonight from this book called Astrophysics for People in a Hurry by Neil deGrasse Tyson. We will also do a little spiel as usual, covering sort of a background. There's also lots of other books that we utilize, so hang tight and we will get our discussion started, and you can put something in the chat in the meanwhile to say hi. Okay, I will say hi to everybody as much as possible, and then I will do the topic and kind of focus on that, and then I will come back to the comments. Okay, I am got something in the microwave. I'm gonna grab it and come back. Thank you all for joining. This is a live, by the way. The live chat hopefully should be working. I know there were some issues last night, so I hope that I see many of you joining, and please do like and subscribe. Can we get 10 likes? I see one. I see one. Hello, Mark 1756. Hi, Mark. How are you doing? Hello, dear, says Mark. Delaware is saying, hello, that's me. Thank you, Delaware. Can we get 20 likes? Don't feel shy to put something in the chat and give us your like. We really appreciate it. Thank you, darlings. You guys are so sweet. You are hesitantly giving us some likes. I appreciate it. Hello, Emir, Mir. Hi, how are you? Doing well. Where are you from? John is saying shame or same. I like your voice. Hello. Thank you, guys. Oh gosh, this mug is quite warm now. So I will be having this drink of mine and looking at the comments, guys. So not to worry if you're joining and would like to get a shout out before we start our topic today. Topic of tonight, we will certainly give people some shout outs, okay? And apologies once more because my lighting is a little off because one of the light bulbs has indeed given up. Thank you for subscribing. Where are you from? Some of you are asking. You should definitely stay in the chat to learn more about my origins because that is quite a hot topic here on these lives, and I go live quite often, and all of those live episodes are posted under the live tab of the channel, so you will see that I'm not lying when I say that it is a topic of debate where I'm from, but I'm currently in Boston, my loves. Cassio! Cassio, my friend from the Dominican Republic, who is currently here in the US, in New York, and who is an old friend of the channel, has given us a super chat of $20. Cassio, muchas gracias. And thank you so very much, and thank you, universe. This quarter, I do need help. I'm having a rather rough quarter right now. But what with tax seasons and whatnot, somehow the government, thinks I made money because I did a Roth conversion. But of course, if you're not over 59, that means that you don't actually get that money. But I am, let us say that I am, there is a lot of pressure on me. There's pressure and I'm underneath it, So I do appreciate your help so very much, my dear friend. Hello, hello, hello. There is a lot of boulders and I'm underneath it, trying to go like this. I laugh, but it's really not funny. I've been spending a majority of this month trying to figure out my accounts and taxes and things like that. So anyways, I will not bore you with that, but that is where I've been this week. Earlier this week, I had to do a lot of paperwork and accounting and taxes. And I really appreciate everybody giving so much love to the videos that have been coming out. I saw some of my premieres. People were showing up for the live stream or the live chat and leaving me comments, which I very, very much appreciate always. So this is a live, like this is an in real time happening, a live. Dominicans are American in my opinion. Hi, Acacio. So Dominican Republic, I do believe, is their own country. Puerto Rico is is part of the U.S. Is a territory of the U.S. But Dominican Republic, DR, is I think their own country. But of course, we are neighbors nonetheless, and Acacio lives in the US. So either way, I just wanted to introduce my friend. Hello, everybody. Thank you so much, Mark, Delaware, okay. Emir, John, Squirrel, Rishabh. Physics is hard. I love that. Yes, indeed. We will talk about physics tonight as usual, and it will be I think you'll love the topic for tonight, by the way. It's a pretty well-loved topic on this channel. We've covered cosmology quite a bit, and this is dark energy. The true to the title here, which is my default title at this point. We thought we will cover it one last time from Neil deGrasse Tyson's book, and also, do our commentary on it. So that's what we're gonna do tonight. John is saying hi there. Amir is saying, I'm from England, by the way, I'm good. Oh, very nice. Welcome to England. Welcome to everybody. Never been there before. What do you talk about? So I talk about physics, astronomy, astrophysics, and cosmology. Welcome to the channel. Welcome to all my continents, including South America, North America, Africa, Antarctica, Europe, Asia. My favorite, of course, Antarctica, Australasia, Australia, New Zealand, welcome, welcome, welcome. Have I missed anybody? Africa, once again, because I love Africa. That was the last continent I've been to, besides, this one, North America. Let's see. Did I miss anybody? All the oceans: Arctic Ocean, Southern Ocean, Atlantic. If you're in the Atlantic, welcome. Pacific, most of the earth. Pacific, welcome. Indian Ocean, of course. Where I'm from, Indian Ocean, also welcome. Everybody, please do feel very welcome indeed in this chat. Dominate the chat. This is neither a tea nor a coffee. This is a malt beverage, whatever that means. I bought this a while ago and I mixed it with some milk and I'm having it as my post-gym little drink as I chat with you guys. So that's what this is. It's malt with a tiny bit of coffee in it and milk. I do have tea and coffee in the kitchen though. Dominicans love listening to music at very high volume. Is that right? You are completely right. Dominican Republic is an independent country. PR. Yeah, see, I think I was right. Puerto Rico is a territory, but Dominican Republic is its own country. Didi, where are you from now? Hello, John. I'm in Boston. Hello from Mississippi. Oh my goodness. Hello to Mississippi. I think that is one of my 17 states or 16 states now that I've never been to. Although I've been on the Mississippi River, on it, not in it. I've been on a boat on the Mississippi River, which of course starts, I believe, in Minnesota and ends in the Gulf Ocean, whatever it ends in Louisiana, where it drains into the Gulf, I think. Correct me if I'm wrong, but I have been on that river in the city of NOLA, New Orleans. I have to say England, especially London, is a place you can tour in an hour. I love London. I try to go there as much as possible, which of course is not very often, but I love it there, and I have been on many tours there, and it is lovely. So let's see. What other? You guys, I am catching up with your comments. Please bear with me if I'm late to your comment. I really appreciate you dominating the chat, though. It is much appreciated. Hi, Leroy. Hello, Kale Blanc. What is your Q? I'm not sure what that means. Mississippi is such a beautiful state. Just got to find the pretty parts of it. It has goods and bads, just like everywhere. You'd probably love it, actually. How's your week? It's going. I've been doing taxes. And yes, I am a little tired. I was at the gym today, which was nice. That was helpful. How are you guys? How are you? I have many knots in my hair at the moment, so I put it in a ponytail. Usually I have it down. But, I am having quite a week. There has been shock after shock with the taxes. I have never been to Tennessee. You're the only 10 I see. This is Boston, where we're streaming from. Hello, Shadow. Hello, Michael. Hello, Avinash. Hello, Daniel. Happy Wednesday. I have to say England, especially London. Hello, you're so pretty. Thank you, Conghost. Dominicans love listening to music. Oh, that's right. Tea or coffee, beautiful eyes. Thank you, Aries. My profile picture. Oh no, Ethan. English, hello. Ethan, can I tell you something? Yes, what is it, Ethan? Adam is saying, Adam, how are you? I saw you were at my other videos. Thank you so much, guys. If you, by the way, catch my premieres that are basically the videos showing my physics classes and going through topics with you with the live chat, but it's not a full live, as in it's a pre-recorded video, but with the live chat. So that's a premiere, and I did see you, I think, on there. So Adam, thank you so much for doing that and participating and stuff like that. So if you see one of those videos, please do show it some love. It really helps me out and appreciate it. But this is a live. So whatever you're saying, it's all happening in real time, okay? Hello, Mr. Avinash again. John Marston, hello. Squirrel, hello. Acacio, once again, thank you so much, my beloved friend. Never been here before. Okay, thank you, Mark, for subscribing. Hello, Rishabh again. Thank you, Squirrel. Okay, I think I caught up with the... Hi, Ben. Oh my goodness, Ben is here. Thank goodness. Ben is my one of my mods who is generally very helpful on the channel. So thank you, Ben, for joining. Tennessee, welcome. Enough of the crap, okay? Leroy, hello. People from countries like Cuba and the Dominican Republic speak English with an accent. Okay. Says Amir, should I take another shot? Go ahead. Get your snacks and drinks for the live, okay? Do you also know Spanish? I know a few words in Spanish. Thank you for being here. All around perfect. Thank you, Patrick. Patrick Moore. I feel like I've seen you before. Who are you? Hello, brah. Hello, Eric. Completing your taxes has put a nice glow. Hello, Northern Versus. Well, I'm a little overwhelmed because I owe taxes and I didn't think I would because, you know, I'm started a new endeavor where I don't feel very rich at all. But because I did a couple of things like a Roth conversion, indeed I owe taxes, and it's quite overwhelming because I don't actually have the money. So I'll have to figure it out. I have to make the money to then pay the taxes for last year. So it's quite an adventure, if you will. But thankfully, I don't foresee this happening again because that particular conversion I did, I don't think I would do again, ever. Oh my goodness gracious. But yes, I am done with the taxes, and because I filed now, which is quite early, I get a discount and I use TurboTax, self-guided. So I got the discount and I got it done, but now I owe money, which is going to be very not fun. Thank you, Northern Versus. Hi, Eric. Lovely nails. Lovely nails. Okay, well, I'm glad you like these nails. They're not done, and I won't have money to do them either because I owe taxes. Hello, Jeffrey. Hello, Tonio. Hello, Bonnie, Scotland. Hello, James from Scotland. Welcome to Scotland. You know so much about physics. What do you do? I talk about physics on YouTube. You should go see all my videos and live streams that are posted under the live tab of the channel, as well as under the videos tab of the channel. And you should come to every live to figure out what it is that I do, my love. Hello, Skelly. Hello, Tagon. Hello, DCI. Stay there carefully. In Boston? You look cozy. I am cozy. I'm wearing my cozy sweatshirt jumper situation. I'm a retired architect, but I always regret not having studied physics more deeply. Well, Mark Preston, you are in the right place. We will learn physics together here. I teach many, many topics of physics, so you should subscribe so that you should so that you get notified every time we go live, and your unfinished physics dreams will all come true. Have you written a book? I have. They're on Amazon if you're interested. Ben is saying we have few Hispanics here. You look phenomenal, babe. Oh, well, John Doe, Jane Doe, everybody, all the does, thank you so much and welcome so much to the live. Welcome one and welcome all. I am glad that you find me phenomenal tonight because I have been a little bit under pressure. So, thank you indeed for your kind comments and continue to dominate this chat. Whether you're from Dominican Republic or not, try to give us your love, okay? Hello, Tyler. It's not that cold right now. It's only like 30s right now. Thank you for the for the physics. Thank you for the gifts. Sometimes I read something and I'm also saying something. I'm getting it all mixed up. Hello, H1. I will drop everything and watch you when I get the notification. Please do. It is highly recommended that you drop everything and watch me and my lives and my videos as soon as you get the notification, and do subscribe. Thank you. Is biology physics? No. Physics is its own subject, and we do well. There might be some, overlap in some parts, but generally speaking, it's its own physical science and basic science field. Okay. Hello, Olivia. Hello. Hi, Harry. Hello, Raiden. Please subscribe. Why so much rich girl attitude? It's okay. You know what you should, Raiden? You should do a super chat. And show us some love and make us richer during this excruciating tax season. Thank you so much. Hi, Justin. Holding hands is cuddling. Hi, Joshua. Oindri has a good diction in Spanish and natural melody and inflections in Spanish. She is... she can... Okay. Languages. Many languages. She has a good ear. Should be a musician. Oh, thank you. Thank you. I did take music classes in college because I did want to be a musician. It's one of my unfinished dreams, actually. Let me start a goal. And Acacio, did I tell you how happy I am to see you? You are... Hi, Benjamin. Hi, Greenland. So I do consulting and content creation. That's my job. That's my business, actually. I did complete a master's in physics. Hi, adorable. Hello, Sam Marone. Where are y'all at? Yes, please ask everybody where they're from. Northern California, it's sprinkling outside. Music, divine mathematics, she's probably a natural. She is using her intellectual resources elsewhere. Okay. Well, thank you so much, millionaire. So I actually have a PhD in physics, but the master's was part of the program as well. So to answer the question, do I have a master's? Yes, I do. Hello, Doc Patriot. Did you guys like and subscribe? Can we get 50 likes, please? Thank you so much. Really appreciate you guys. Do I have Spotify? Thank you, Ben. Appreciate you. Okay, thank you so much, everybody. I'm gonna check on settings over on this side, and then we'll start the topic without too much delay here. So remember that we speak on this channel, we talk about cosmology, physics, astronomy, and astrophysics. Thank you for subscribing. Some days we focus more on one than the other. Cosmology is, of course, the study of the universe as a whole, and so it's much more of a larger scale type of physics so cosmology, I would consider that sort of a subtopic within physics, where we're now considering large scale and basically this universe at large, and not just something local or relatively local, because everything, large and small are, of course, relative. But I would, consider our galaxy or the local cluster in which our galaxy is part of to be local in cosmology, whereas larger scale as far as how this universe has a distribution of matter, which gives it the large scale structure, which is not random, and how that happened, or a topic like the Big Bang, how our universe got started, or how the universe has been evolving, and things like that, or the expansion of the universe, a very relevant topic. I would consider those cosmology, which is the study of the universe. It affects things that are more large scale and really part of the universe topic. Okay, and also. I wanted to remind you that, of course, some of the topics we've covered, like dark energy, dark matter, can have some of them, not all of them, can have some overlap with the other fields as well. So dark matter, which is of course this extra matter that we find, that we have evidence of gravitationally, but that does not interact with light, and so we can't really see it. We don't know exactly what it is. Is it some new form of particle or some other thing? That topic, because it's a current research topic, that topic actually really is in the cross section of astronomy, cosmology, astrophysics, and such, even particle physics, right? Because if you were to try to understand the particle nature of dark matter, and you wanted to do some experiment, and you're probing that, then it's could be understood as a particle physics question. Or if you're sort of trying to understand dark matter within the realms of our own galaxy, like the Milky Way galaxy is also affected by dark matter, right? Then I could call it maybe something like astronomy, right? But then if you are considering the role of dark matter in large scale structure, which is basically how the smooth universe, way back in the early universe, had these basically fluctuations and overdensities in it. And those overdensities were basically gravitation winning in some spots. And those led to the first galaxies, stars, and things like that, which is why we are here. If gravitation never won, then there would be no galaxies and stars would not have lived and died to make the next generation of stars, and the next, and gas clouds that basically condensate to make something like our solar system. So we really have gravitation, and whoever helped galaxies to form in the first place, because there were no galaxies in the early universe. So whatever phenomena formed the first galaxies, which of course also formed the first stars and such, whatever phenomena that is in the universe, because this affects the universe at large, we have much to thank that for, because without that we would not be here. Okay, so there is sort of a notion that there might have been dark matter, a role that dark matter might have played in that phenomena, in that process, basically where the first galaxies may have formed with some help from these extra matter, which interacts gravitationally but does not interact with light, does not do nuclear fusion, seems to be quite the mysterious type of matter. And of course, there are papers being written all the time. There are people doing research even now, current topic here, on what this dark matter is. So this dark matter, in this regard, is a topic in cosmology as well. So it is a topic that really transcends many subfields of physics. A lot of subfields of physics are affected by dark matter. But what we are about to talk about tonight is actually not dark matter. So you might be like, why is she talking about dark matter so much? Well, because dark matter, the topic of dark matter does come up with regard to this other topic as well. It is not something you can really forget about or ignore when you consider the universe as a whole. So I wanted to mention dark matter because it is an important cosmic ingredient. It is the second most important cosmic ingredient. But tonight's topic is the first most or the most important cosmic ingredient as far as we understand in the current stage of this universe, and that is dark energy. So I wanted to contrast dark energy with dark matter because, as I've been saying so far, dark matter is a topic you can study with all those different fields: astronomy, cosmology, astrophysics. But dark energy is really much more of a cosmology topic. So if you really say, if you didn't care about cosmology, I don't know why, because it's the most coolest, really, field out there, then you wouldn't really care too much about dark energy, because dark energy is the cosmic ingredient that leads to the expansion of this universe. So, the expansion of the universe, and that is not a local effect. That is not an effect that we see in the scales of this galaxy or the next galaxy or the neighboring galaxy or in this cluster. That is an overall universe, the full thing kind of effect. So, exactly what this dark energy is and whatnot would fall squarely in the cosmology topic. And there would have to be those types of approaches that really allow for large distance type of measurements and things like that. If we're not suitable for measuring, say, redshift data or picking up on signals that are from the most distant galaxies, the most distant galaxies, as far away as possible, then pretty much it's going to be challenging to probe exactly why the universe is expanding. Because, over 100 years ago, of course, when this topic kind of got introduced in a mathematical way for the first time, was actually in Einstein's equations for general theory of relativity, when he introduced something called cosmological constant. Now, he was doing it to balance out gravitation in the universe. He figured that, well, general theory of relativity is the theory that explains gravitation. It's the upgraded theory for gravitation. But there is this one issue of, this universe is not exactly collapsing under gravitation. It doesn't seem to be collapsing. It seems to be balanced. It seems to be stable, or so he thought. So then, to keep his equations balanced against gravitation, he included the cosmological constant, or a term, to allow for a balanced universe. But this actually went on to be what he called a blunder, because we were shown by Hubble that the universe was not only balanced against gravitation, but it was actually expanding. So it was kind of competing with gravitation and winning. So at larger distances, not the small distances, not at the scale of, anything near us, but at the larger distances or scales of this universe, the universe is actually expanding, not balanced or static against gravitation, but expanding. So this seemed like a big blunder to him, Einstein. But then actually, it turns out that it's good that he introduced that concept or that constant or whatever, because it gives us sort of a mathematical foundation for this very mysterious topic even today. So it's basically a way of saying, well, at least, this concept of cosmological constant was already there. It's nothing new, but we have to kind of update it and upgrade it to our current understandings, which has to kind of match our current observations and things that we find out in the universe as we do measurements currently. So it's always good to kind of, get something started, and even if you're wrong, to iterate on it rather than not have it at all. And that is exactly, I think, the value of the cosmological constant. So that's a little background for you. So as you can see, it's two very different things dark energy has to do with the expansion of the universe, and there's current efforts to, probe that further and understand it further. It's very different from dark matter, and but both of those are mysterious questions still that we would like to have answers for. There are other, very many topics as well. I would say there are actually some topics that don't get as much attention as they should. For example, understanding how all the elements are made in the different processes in the stars. There are some elements, for example, origin of elements, that we understand quite well how they were made in the stars, but some of them we don't understand so well. So that too, I would say, is a top question. So those three: what is dark energy, what is dark matter, and what is the origin of all the elements, I would consider to be the top questions in today's day and age. Okay? Thank you so much. Hi, Michael Bradley. Oh my goodness, thank you so much, Michael, for the super chat. Michael Bradley is saying, thanks for sharing your knowledge on the topic. Of course, it's a passion of mine to do science communication. Of course, this is all my background. I studied all this in grad school, and I contributed to it myself. Especially my field is particle astrophysics, but I also got to learn quite a bit of cosmology, thankfully, and it's the favorite topic to teach and talk about and share with you guys. So thank you indeed for the super chat, for appreciating me, and I appreciate you very much. Thank you, Michael Bradley, and thank you, Acacio. So hopefully this is kind of detangling some of these concepts a little bit, because in these terms, unfortunately, some of the terminology that is used in technical fields like physics in this case, or cosmology, astronomy, the terminology can be a little confusing, and people can get a little lost in things can get a little tangled up when they don't have to. So I would say definitely, if you're interested in cosmology, we have a lot of previous lives on the topic already, and definitely pay attention to videos or lives that I've done before or even now, called Cosmic Ingredients. So basically, this cosmic ingredient situation, sometimes noted as energy density of the current universe, and what is contributing to that energy density, right? Though that's very important. So you have to sort of detangleify the energy density of the universe and what really contributes to it. And pretty much there are actually just 5 things. It's dark energy, dark matter, photons, neutrinos, and baryons, where baryons are the ordinary matter. Now, it's a little bit, I would say, a little bit of a misnomer, in the sense that baryons actually typically, even though in this case they are supposed to capture all of ordinary matter, actually baryons, very strictly speaking, are only protons and neutrons. And of course, ordinary matter also has something called electrons, right? And electrons are technically not baryons, but electrons are a lepton in particle physics, right? So you can also see some of this terminology gets a bit mixed up, because people work in these various different subfields and they might mix and match their words. So just be careful. But basically, in the purposes of cosmology, we actually lump the electrons together with baryons. But that is not technically correct, because they're very different things. Electrons and protons and neutrons are all protons and neutrons on the one side, and electrons are all very different things, okay, in particle physics. But in the purposes of understanding ordinary matter, let's just lump it all together and call them all baryons. That's fine, I suppose. So 5 things that contribute to the energy density of this current universe. And also keep in mind that this universe, much like us and our lives and everything we know and love, is evolving. There is nothing really static in this universe, if you will. Like, even when it was, even from its birth to now, it has evolved. It has gone through various stages. How the universe was when it first took birth in the Big Bang, or which is, you know, the beginning of the universe, is it was evolving then and it is evolving now. So there is nothing that I say today that will become sort of the permanent truth, okay? You have to keep an open mind to things changing. Now, I don't know if things will change or just our understanding of things will change probably in our lifetimes, but pretty much just know that in the cosmos are changing. They're not the same. There was a time when there were no galaxies, and now, see, look at today. We have so many galaxies, and we're part of one, right? We're part of one that I believe is almost as old, not as old, exactly as old, but almost as old as the universe itself. We're part of a very old galaxy. So, but there was a time in the very early universe, you know, even something like 300,000 years old of the universe, there were no galaxies, okay? Because we have a signature, a bunch of photons that are hanging out from that time. When we look at that, we understand about the universe at that time, and there were no galaxies then. So just think about it, right? The universe has changed. It has changed. It's not the same. It was born within like 10 to the minus 41 or 49. Correct me, you know. You have to look this up. Planck era, you know, some very short time, it did a lot of things and changed, evolved, right? And then, you know, it didn't have any galaxies for many years. And now look at it, 14 billion years old, and it has like an infinite number of galaxies. But even then, those galaxies are made of, well, what we can see at least is the ordinary matter, but then we also think that there is this other thing, dark matter, and you know, it changes. So when I say we must understand the cosmic ingredients of today and today's universe stage of evolution, that's what I mean. Don't think of it as a permanent, non-changing truth. It's a changing truth. So right now, as we understand best the cosmic ingredients, the things that contribute the most to the energy density of this universe, of our universe, is number one, dark energy, number two, dark matter, number three, ordinary matter, or sometimes lumped together with baryons, and number four and five are photons and neutrinos. So those are our cosmic ingredients that we have to play with when we try to understand this universe and where and how things are happening here, okay? And whatnot. So that's what's contributing to the energy density. That's what we consider as the cosmic ingredients at this time, where dark energy really dominates a lot. And so because it dominates so much, of course, people want to understand it better. Because that's, as human beings, that's all we can do, is try to understand nature. But nature is changing. Nature has its own mind. So we cannot always know everything. We are definitely far from knowing everything, but we have a curiosity to understand it better, okay? And this dark energy business is such an important cosmic ingredient that it becomes quite compelling to try to understand it as much as possible, okay? Thank you so much for the super chat. Oh my goodness. Who was it? Also, thank you for the gifts. Thank you, Derby, for the gift. Thank you, thank you, thank you. Thank you for the floating heart. Hi, Nate. Nate Escape. How are you, Nate? I haven't seen you in so long. Hello, Nate. Sent a gift. Thank you. And then someone else had done. Where did it go? Hi, Ryan. Thank you so much. Hi, Ryan. Are you from New Zealand? Welcome to the channel, to all of New Zealand, Australia, Antarctica, that whole place. Love it. Ryan is saying, hello, I'm new and like intelligent people. Well, thank you so much. And please do join, and you should subscribe. You give us a like. Thank you for the super chat. Really appreciate you. You should Subscribe and come back often because we have these types of discussions quite often, okay? And they make more sense when you keep returning. I like this. Detangle the chicken piccata or chicken tikka masala. Oh my gosh. Yes, so dark matter forms halos. So dark matter, good. Great. Some people are chiming into the comments as well. So hopefully that kind of helps in terms of understanding the importance of dark energy. Okay, why we're talking about it today. And please don't mix it up with dark matter because that is not the same thing. And dark matter is the second most dominant ingredient of this universe, not the first most or the most. The most is dark energy. So we will talk about that. Hi, Thomas. Somebody said about the matter thing. I just wanted to give you the caveat that ordinary matter includes, of course, protons, neutrons, electrons, and whatnot. Just don't, when I club electrons under the baryons in cosmology, just keep in mind that in particle physics, electrons are a very different family of particles than protons and neutrons. Okay, that is all there is to it. If you don't want to feel confused about that because this is too much detail, then that's totally fine. I would just say the cosmic ingredients then are dark energy, number one, dark matter, number two, ordinary matter, number three, number four, photons, and number five, neutrinos, okay? And just keep it simple, where ordinary matter, of course, includes electrons as well. Electrons, positrons, things like that, okay? But of course, we go into the details of exactly what these things are a bit more when we consider particle physics, which has a nice little family for each of these particles, the ones that are in the standard model anyways, okay? So for example, if dark matter's particle nature was discovered, we'd have to basically add it to our particle physics knowledge, okay? All right. But I wanted to say that don't confuse the particle families. But it's okay. All right, so we actually started this topic from the book already, so we will just continue from there. Hi, Texas. Why do I feel like you're very condescending in real life? Oh. Hi, Mr. G. Hi, Morpheus. Hi, Boo Boo. What do you not understand? Let me know your questions. Dark matter is different than dark energy, okay? Amit. Hi, Farid. How are you doing? Sure thing. You can email me. Hello, Warren. Hi, Gabriel. So positrons are also in the lepton family. Positrons are the antiparticle for electron. So cosmologists may club them all together under baryons, but technically speaking, electrons, positrons are not exactly baryons, okay? But whatever, they're part of the ordinary matter. Hi, something more to look forward to. How are you doing? I saw your comments on my other videos. Thank you so much. Please do, whenever you see my videos that are premiering and there's the live chat, please do show it some love. I really appreciate it. And I did see your comments. I'm happy that I caught you here right now. How are you doing? Something more to look forward to. And that's quite an interesting username. From electron eddy current formation. Hi, Crazy Sick Wine. Very good job, Ben. I love Ben's comments. According to the Lambda CDM model, the universe is roughly 5% baryonic matter, 27% dark matter, and 68% dark energy. So that 5% baryonic matter also basically includes all of the ordinary matter, which is what we were mentioning. So thank you for that. And by the way, in cosmology, you can have various different models. Basically, the one that, of course, matches with observation and everything the best would be the one that wins. But you can kind of dream up your type of universe, if you will. Hi, Kevin. Felix is saying you look tired today. Hello. Can we get 100 likes? Hi, Mohammed. What's your question? Thank you. Oh my gosh. Okay, so let's keep on going. Now we will hear from you guys' favorite, Neil deGrasse, okay? Let's do that. I wanted to give you that upfront little spiel because it kind of can help to anchor the topic, give you a base, okay? And now we will read Neil deGrasse Tyson's Astrophysics for People in a Hurry, his chapter on dark energy. So it's not just me that you're hearing from, it's also deep voice Neil deGrasse. Okay? So, okay. All right, actually, we'll skip this part. Let's go to Friedman. Okay, so you already know that Einstein had created the universe where that neither expanded nor contracted because he introduced the cosmological constant with the motivation of balancing out gravitation, not necessarily thinking that the universe might actually be expanding, which happened to be the case. Now let's come to Friedman, okay, very important person. Russian physicist Alexander Friedman would subsequently show mathematically that Einstein's universe, though balanced, was in an unstable state, like a ball resting on the top of a hill, awaiting the slightest provocation to roll down in one direction or another, or like a pencil balanced on its sharpened point. Einstein's universe was precariously perched between a state of expansion and total collapse. So basically, this static universe was actually quite unbalanced. It's like basically saying between expansion and between collapse, I am here totally precariously balanced, you know? So Friedman did a lot of work with this expansion and universe model business. And so that actually helped us a lot. And by the way, we have done a live in the past called Friedman equations. We've done a bunch of different lives on this topic. So you can always find more. Okay. Thank you once again for the super chats, guys. I really appreciate it. Okay. So, moreover, Einstein's theory was new. And just because you give something a name does not make it real. Einstein knew that lambda, as a negative gravity force of nature, had no known counterpart in the physical universe. So he came up with this, he called the cosmological constant lambda. So we still kind of use that word or that symbol lambda for dark energy, which is also, dark energy is the new name for basically the cosmological constant. He used this and he put this into his math, but that did not mean that he was happy about it or understood it physically. And that's exactly the case even now. We have gained more insight on the topic, but we would also still like to understand what it means really physically, this lambda, or this what we call now dark energy. Okay. Einstein's general theory of relativity radically departed from all previous thinking about gravitational attraction. Instead of settling for Sir Isaac Newton's view of gravity as spooky action at a distance, a conclusion that made Newton himself uncomfortable, general theory of relativity regards gravity as the response of a mass to the local curvature of space and time caused by some other mass or field of energy. So it's a much more sort of elegant, bending of space-time that's happening due to a mass, local curvature of space and time caused by some mass or field of energy, which is really gravitation. It's not some like instantaneous or, spooky action at a distance thing, which is kind of what Newton did. But it's okay because, again, Newton's gravitation theory is approximately correct. So Einstein's equations showed that as an approximation, you get Newton's gravitation from it. So it all kind of worked out. But Einstein gave us the deeper insight and gave us the better explanation, or the more newer, updated explanation for gravitation. And, it explained it as a local curvature of space and time. In other words, concentrations of mass cause distortions, dimples, really. So it's like a little dimple in space and time, okay? And let me show you what a dimple is. So if space and time I want to show you this. With space and time, so I've got this cushion. If space and time is this cushion, then a dimple in the cushion is gravitation, okay? So basically consider space and time in that kind of way. I know the pillow does not have the same dimensions as what we need in GR, but if space and time was basically the dimensions and whatnot, then a local curvature of it, or a dimple in it, is literally the gravitation of some mass or field there, okay? So massive objects cause these types of dimples in space and time. You cannot consider space separately than time separately than space, but basically these massive objects like a black hole, a star, even the sun in our solar system is causing a dimple in space and time and changing the curvature of space and time. And because of the dimple, we go around the sun. Space and time has been curved in a way where we go around the sun. So in general theory of relativity, gravitation is not a force, and there's no like, it's not an acceleration. It's a geometry of space-time, which has been dimpled, geometrified by a massive object. So in our locality, really the dimple causing thing is the sun. It has a lot of gravitation, and it causes a dimple in space and time and bends space and time in a way where we find ourselves going around the sun and the other planets doing the same, okay? So it's not explained in terms of a force and like the centripetal acceleration and all these different dynamics or laws of physics dynamics that Newton had done. Although those things are useful as an approximation, and we don't want to, undermine those things, but those things are ultimately less correct and less accurate than general theory of relativity. Okay, so it's the cushion example. That's just an analogy. Of course, space-time is four-dimensional. The cushion is three-dimensional. But if you had a cushion basically that represented space-time, then the dimple would be gravitation. Okay, and see how I made a dimple. And say like if there's an ant on that cushion, the ant would kind of go into the dimple, and the ant would, it would seem like it's accelerating or changing sort of its trajectory or something. But it's basically just following a straight line in in a geometry that has that dimple. Okay, so that is what it is, and we've also talked about this, but this is Riemannian geometry, not Euclidean geometry, when we do the four space-time and GR. Okay. All right. So concentrations of mass, like our sun, like a black hole, like a star, etc., in their locality, will cause distortions, dimples, really, in the fabric of space and time. These distortions guide the moving masses along straight-line geodesics, though they look to us like the curved trajectories we call orbits. So just like in the cushion, like I was saying, an ant on the cushion would go into the dimple and it would look like it's taking sort of a curved path. Actually, it's kind of following a straight line, but in the curved geometries, the curved space-time. So same thing we do, actually. Us, the Earth, and the other planets, we're actually all following the straight line version or a geodesic, but in general relativity, which has four space-time and a different geometry than what we're used to. So in Riemannian geometry, we are actually kind of going on a straight line. But the straight line, I'm putting air quotes on the straight line because it's not straight in Euclidean geometry, it's straight in Riemannian geometry. So we call it a different name, we call it geodesic, and we follow that there under gravitation, okay? If there was another force, we would have acceleration, but actually gravitation just lets us follow these geodesics. So the Earth moving around the sun, that orbit, it can look like a curved path that it's taking, but it's actually taking the straight line in Riemannian geometry, okay? The straight line in general relativity. So of course, you can imagine general relativity came up with all this math and insights now, but if it did not produce the correct orbit of the Earth around the sun, for example, according to what we know and according to Newton, then of course it would be a failure, and it did. It did reproduce Newtonian mechanics as an approximation, as an answer that comes out if you are okay with an approximation. And so it was consistent with what we already knew. So, it's not just that he came up with a bunch of math and was like, okay, bye-bye. No, he has to actually show that that math actually works and gives us, for example, the Earth's orbit around the sun falling out of GR now, not falling out of Newtonian mechanics because it already did that. So those types of things are some of the victories of general theory of relativity, okay? And so this is also to say that general theory of relativity is very successful. It's been successful now for over 100 years. Many predictions of it have come true. So if GR, or general theory of relativity, if it's not giving us an explanation of something, then it is not immediately the case that GR is obviously wrong, because GR is very successful in many ways. And so we'd have to really understand, like, okay, this dark energy business, this expansion of the universe business, we didn't quite get this from GR. We started to get it in the sense of, like, we started to have this concept of the cosmological constant. But if dark energy or the expansion of the universe is something that is not obvious to us from GR, then we do need to take a closer look. And this is a really hard problem because Einstein's theory is very successful in many ways, okay? So, all right, so these distortions guide the moving masses along straight line geodesics, though they look to us like the curved trajectories we call orbits. Geodesic is a needlessly fancy word for the shortest distance between 2 points along a curved surface. So that's what a geodesic is. It's not anything too fancy. Shortest distance between 2 points along a curved surface, extended in this case to be the shortest distance between 2 points in the curved 4-dimensional fabric of space-time. So geodesic concept, shortest distance, 2 points, curved surface. But then, of course, it has been now applied in general theory of relativity. It has been applied to the 4 space-time, okay? So Einstein took space and time and treated it as the 4-dimensional geometry that you need there, okay? All right, so the 20th century American theoretical physicist John Archibald Wheeler said it best, summing up Einstein's concept as matter tells space how to curve. Space tells matter how to move. It's really space-time, okay? So matter tells space-time how to curve, and space-time tells matter how to move, which is a nice little summary of all the above. Has something more to look forward to. Thank you so much. I'll keep going and then I'll come back to your comments, okay? I'll keep going with the topic for a little bit longer and then I'll look at all your messages. So keep them coming. At the end of the day, general relativity described 2 kinds of gravity. One is the familiar kind, like the attraction between Earth and a ball thrown into the air, or between the sun and the planets. It also predicted another variety. It indirectly kind of predicted another variety, okay? A mysterious anti-gravity pressure associated with the vacuum of space-time itself. So now, because of that cosmological constant that he had to introduce in order to balance out gravity, right? Because of course he was perturbed that, well, we're not exactly collapsing, so what's going on? So he introduced the cosmological constant as an anti-gravity term. So he indirectly gave us this concept of an anti-gravity term, and he indirectly introduced to us this concept of an anti-gravity something in this universe, which is still a mystery to us. So hopefully you're following this part, okay? It's more subtle or not as talked about, but this is really the history of dark energy, okay? So the something which which he thought balances out gravity, and really a mathematical term he introduced and called it the cosmological constant, is what has introduced to us really about this whole thing. And we want to understand it better. So it predicted another variety, a mysterious anti-gravity pressure associated with the vacuum of space-time itself. So anti-gravity, because, it's going against gravity, and it's making the universe expand. So it's, what is it? What is it really? But it seems like some negative pressure of the vacuum, where if you had pressure going like this goes like this. You know, it makes the universe expand. So, you know, this is sort of some words that describe it. But once again, we would really like to understand, what is this something something, okay? It's not clear. All right, so Lambda preserved what Einstein and every other physicist of his day had strongly presumed to be true: the status quo of a static universe, an unstable static universe. So they thought that the universe was static, which is fine. Back in the day when they didn't observe as much, you know, when they were still new to observing the universe and getting measurements and whatnot, of course, they wouldn't have known about the extent of this universe, and figured out that it was not static. Okay, so cannot really fault them for that. To invoke an unstable condition as the natural state of a physical system violates scientific credo. You cannot assert that the entire universe is a special case that happens to be balanced forever and ever. Because, you know, being balanced would be a special case of the overall more general case. You cannot assert that one. Nothing ever seen, measured, or imagined has behaved this way in the history of science, which makes for a powerful precedent. 13 years later, in 1929, the American astrophysicist Edwin Hubble, so this is the Hubble guy that I mentioned, by the way. Hubble is so very important, maybe the most important person in astronomy. I don't even know. Like, you know, he gave us, he really opened our eyes into the universe and gave us so many measurements and observations, and you know, showed us that there were so many other galaxies and whatnot. So without the very important contributions observationally from Hubble, we would really be nowhere. So do take a moment to appreciate that Hubble is very important, okay? And of course, we have a telescope named after Hubble as well, but that telescope is quite old at this point. So, but everybody wants time on Hubble. When I was in grad school, and the theoretical astronomers were always wanting time on Hubble, as in time on that telescope, okay? So, there's a fuzzy. Hubble discovered that the universe is not static. He discovered the expansion of the universe. Isn't that so cool? I feel like this is not given enough. This is not enough credit. He should get so much more credit. Hubble gave us that the universe is not static. He's an amazing discovery, really. He had found and assembled convincing evidence that the more distant a galaxy, the faster the galaxy recedes from the Milky Way. So the more distant the galaxy, the faster it was receding from our galaxy. Now, embarrassed by the cosmological constant, which corresponded to no known force of nature, and by the lost opportunity to have predicted the expanding universe himself, Einstein discarded lambda entirely, calling it his life's greatest blunder. So he got a bit flustered to realize that the universe was in fact expanding and not static and balanced, okay? Poor baby. Everybody makes some mistake or other, so it's really no big deal. And, you know, when you make a mistake, you give others opportunity to contribute, such as Hubble. So good he did that. Make some mistakes. I think in scientific discourse, we must do things, try things, make mistakes, move on, and update, you know? That's all we can do. So anyway, by yanking lambda from the equation, he presumed its value to be zero. such as in this example, assume A equals to B plus C. If you learn later that A equals to 10 and B equals to 10, then A still equals B plus C, except in this case, C equals 0 and is rendered unnecessary in the equation. But that wasn't the end of the story. Off and on over the decades, theorists would extract lambda from the crypt, imagining what their ideas would look like in a universe that had a cosmological constant. 69 years later, in 1998. So this is now, we're jumping forward to 1998, where things get very interesting. Okay, let me get a sip of water. I'm thirsty. Thank you, guys. um, okay, I'll be right back. Let me fill this up with water. Thank you for helping with my super chat goal. That is so nice of you guys. Hi. I see John Doe's comment. You are so beautiful. Thank you. Hi, Daniel. Didn't someone say I look tired? uh, whew. Hi, everybody. Thank you so much for all your comments. I see them and I'm delighted. Thank you. I see them and I am delighted. I am filled with delight. Something more to look forward to had commented yesterday. I can't believe I missed your live chat tonight. I am so like, I cannot believe this. Oh, I miss you. It's not fair. Wow. I didn't know that my life was so important to you. Thank you so much for your kind comments and appreciation. Really appreciate it. I wish you can go live right now for just a little while, but I understand you have to get your rest. I was actually doing my taxes. So thank you for understanding. I wish I was getting rest. I've been so tired, guys. Thank you for noticing. Reese said, that guy has a good memory for sure. Hope you're okay. Well, Reese, I hope you're seeing me live right now and understanding how things are. But thank you, guys. I wanted to acknowledge I do read all your comments and they're delightful. Delightful. In fact, sometimes the best part of my day, other than, of course, my babies, my universe. It's your kind comments. Milky Way fun facts. I can't believe you just left. Oh gosh. Thank you for watching the videos that are premiering regularly and has a live chat. Thank you also for being here on a live, in real-time live. But if you see those other ones, thank you for watching and commenting. Really appreciate it. Newton versus Hubble 2026. We are the people. Hello, Adam. Hello, Farid. Hello, Siradam. Hello, Fargo Michael. Hi, Joshua. Thank you. You're awesome. Thank you for this. Thank you so much. Please subscribe. Do I have a necklace? I do, but I'm not wearing one. It's cold. I have this mostly up, but also. Am I related to Hubble? Not that I know of. My PhD academic tree actually includes Fermi. I'm related to Fermi and Chamberlain. Yeah, so I don't think I'm, not that I know of. I'm related to more of the particle physics side of things through my advisor. So in, in academia, we have like academic family trees, like your advisor, their advisor, and their advisor, and their advisor. That's basically your academic lineage. So because of my advisor being from basically, well, I guess she's from particle astrophysics, but I think her advisor was more of a particle physics. So I'm related to Fermi, a few steps up, not Hubble. Hi, Northern Verses. I don't have hot chocolate right now. just needed some water. I'll continue here. My ring. This is my usual one. And then these are rings I got myself from a jeweler I know. Do I have a tortilla warmer? Back to it. Okay. So Einstein was a bit embarrassed that he did not predict an expanding universe like it actually was, but Hubble did it. Well, Hubble found it. But then what happened in 1998, which was 69 years later, okay? Science exhumed lambda one last time. Early that year, remarkable announcements were made by two competing teams of astrophysicists. So this is what we've mentioned and gone over in other lives. Keep in mind that this stuff from 1998 is not to be taken lightly because competing groups of astronomers, astrophysicists worked on this stuff. So they didn't have to agree with each other, okay? So keep that in mind. So anyway, these two competing teams were, one was led by Saul Perlmutter of Lawrence Berkeley National Lab in Berkeley, California, and the other co-led by Brian Schmidt of Mount Stromlo and Siding Spring Observatories in Canberra, Australia, and Adam Rees of the Johns Hopkins University in Baltimore, Maryland. Dozens of the most distant supernovas. So this is that supernova data set that they used and that they studied and got these results from, and competing groups of astronomers did this. So again, what they found is very, striking. And so let's see. Dozens of the most distant supernovas ever observed appeared noticeably dimmer than expected, given the well-documented behavior of this species of exploding star. Reconciliation required that either those distant supernovas behaved unlike their nearer brethren, or they were as much as 15% farther away than where the prevailing cosmological models had placed them. The only known thing that naturally accounts for this acceleration is Einstein's lambda, the cosmological constant. When astrophysicists dusted it off and put it back into Einstein's original equations for general relativity, the known state of the universe matched the state of Einstein's equations. So they basically had taken out this lambda, and now, lo and behold, they have to put it back and they have to use it to account for this expansion and the data that they're seeing from these dimmer supernovas, okay? And by the way, we have talked about this in a lot more detail in other lives if you look for it, okay? The supernova data, even I think several lives ago, just recently too, we've talked about it, okay? It's a famous data set. And 1998 at this point is not even that recent, so this is quite well established observational analysis, okay? The supernovas used in Perlmutter's and Schmidt's studies are worth their weight in fusionable nuclei. Within certain limits, each of those stars explodes the same way, okay? Igniting the same amount of fuel, releasing the same titanic amount of energy in the same amount of time, thereby reaching the same peak luminosity. So this type of thing, the luminosity is very important here, peak luminosity, and sometimes these things are called standard candles in astronomy, okay? So they know what they're doing with using these sources as standard candles. They are the same type of things that are happening, okay? So they serve as a kind of yardstick or standard candle for calculating cosmic distances to the galaxies in which they explode out to the farthest reaches of the universe. Standard candles simplify calculations immensely. Since the supernovas all have the same wattage, the dim ones are far away and the bright ones are close by. So this peak luminosity business and this all of this stuff about the standard candle, this is quite common. They use this way of knowing and comparing these luminosities, okay? So standard candles, they simplify calculations immensely. Since the supernovas all have the same wattage, same explosion, same type of energy coming out, same amount of fuel releasing, same amount of energy, same wattage, same power, should have the same luminosity. So the only thing is that is the cosmic distance. After measuring their brightness, a simple task, you can tell exactly how far they are from you and from one another, okay? If the luminosities of the supernovas were all different, you could not use brightness alone to tell how far away one was in comparison with another. So this is why it's very important to use standard candles, because you don't want these types of differences in luminosity, okay? A dim one could be either a high wattage bulb far away or a low wattage bulb close up. All fine, but there's a second way to measure the distances to galaxies: their speed of recession from our Milky Way. Recession, that's part and parcel of the overall cosmic expansion. As Hubble was the first to show, the expanding universe makes distant objects race away from us faster than nearby ones. So the ones that are farther away are actually getting farther more fast than the ones that are closer, okay? Which is what Hubble had shown, which is pretty really interesting, really intriguing. So by measuring a galaxy's speed of recession, another simple task, one can deduce a galaxy's distance. If those two well-tested methods give different distances for the same object, something must be wrong. Either the supernovas are bad standard candles or our model for the rate of cosmic expansion as measured by galaxy speeds is wrong. Well, something was wrong. It turned out that the supernovas were splendid standard candles. Like, as far as the supernovas being good candidates or not, that's all good. Astronomers have been doing this sort of thing forever. And also, these were multiple groups that were working on this, so they didn't have to, agree. It would be pretty weird to make the same exact mistake, that sort of stuff. It turned out that the supernovas were splendid standard candles, surviving the careful scrutiny of many skeptical investigators, and so astrophysicists were left with a universe that had expanded faster than we thought. So this expansion that they thought would be there was wrong. It actually expanded even faster than we thought. So this is where that accelerating expansion is happening, but also the expansion is accelerating. This news kind of comes from there, from this work. So there was no easy way to explain the extra expansion without invoking lambda, Einstein's cosmological constant. Part and parcel for cosmic expansion. Right. Here was the first direct evidence that a repulsive force permeated the universe, opposing gravity, which is how and why the cosmological constant rose from the dead, because it does oppose gravity. It makes us expand faster than what we would expect. Lambda suddenly acquired a physical reality that needed a name. So really, it's this 1998 supernova's data set where it became sort of real. It became like, oh my gosh, there is something going on here, and now we need a name, and that's when we came up with this name of dark energy. Okay. So lambda suddenly acquired a physical reality that needed a name, and so dark energy took center stage in the cosmic drama, suitably capturing both the mystery and our associated ignorance of its cause. So it's mysterious, that's why we call it dark energy, but also we don't know what it is. Perlmutter, Schmidt, and Rees justifiably shared the 2011 Nobel Prize in Physics for this discovery. So these people all got the Nobel Prize for this. It was not a small thing that they worked on it, okay? The most accurate measurements to date reveal dark energy as the most prominent thing in town, currently responsible for 68% of all the mass energy in the universe. Dark matter comprises 27%, with regular matter comprising a mere 5%. So I told you that the big motivation here is also that dark energy is the most important cosmic ingredient. It is contributing to 68% of all the mass energy in the universe, followed by dark matter, which is 27%, and then ordinary matter is only 5%. So then, of course, it begs the question, what is this dark energy? And we would like to understand it better, and therefore, there's research going on it. So that is that, okay? Now the next part is about critical density and all this stuff. So I actually want to cover that. There's a little bit more to this story with dark energy, and I want to cover that tomorrow because it's a bit more information that I don't want to overload on you today. So worry not, you just have to come back tomorrow for part 2 of this topic, okay? I'll mark the page because this is going to be very interesting. It's not a trivial topic. So we will continue and finish this out tomorrow. And the sort of energy density of the universe and critical density and all this stuff that I was mentioning will be covered in that way, okay? Let me take a look at the chat, and other than that, thank you so much for being here. Appreciate everybody. Can we get 100 likes? Thank you for your comments. Thank you for your support. Thank you for the super chats. See you tomorrow. And please do like and subscribe and share and tell your friends, brothers, sisters all about the channel, and have them come along. I will look at the chat and be delighted. Thank you, guys. Hi, Shona Fuji. Oh. I never tagged the book. Let me do that. Whew. Hi, Boo Boo. How are you doing? Did things make more sense? Hi, Kipper. How are you doing? Hi, Randy. Hi, Nana. Hi, Joshua. Hi, Shona Fuji. Thank you for liking and subscribing. Please do subscribe so you can come back and we can continue to continue. Tag the book. Thank you, Ben. Hi, Just the Images. How are you? Hello, Bud Morgan. It should be around the same time tomorrow, 11 p.m. EST tomorrow. $153. Hi, Nebular. Hi, Joshua. Fuji. No, Shona. Fuji. Hi, Optimistic. Nice cardigan sweater. Yes, this is a cardigan. Fuji is pushing things off of the counter. Because he wants Mama's attention. Hi, Fuji. I see you, Shona. Korana, babu. Ikikata. 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 Hey, Mama loves you, Shona. Hi, that guy. Good evening and good morning to Ireland. When can we expect flying cars? I can't even handle the ones that are currently available, so not sure. Hello, David. Hi, Palak. Hi, Sahil. Excuse me. Did my live stop? Thank you, Music Genetics. Okay. Hi, Mar. Thank you, Kipper. I have a few books, but I do want to write more. Hi, Music Genetics. You look like a man with 2 eyebrows. Farid, can you do a super chat instead of spamming me? Really appreciate it. Okay. Video is live. Chat is pre-recorded. That's so true. I have some pre-recorded videos sometimes that are, with the live chat, but this one is you guys are too funny. Oh. You wrote this in November 2025? Your sweater looks very uncomfortable. It's actually very comfy. It's soft. See, it's plush. It's very soft on the inside and outside. Oh my god, you guys are too funny. Because of the spamming, it's hard to read the comments now. Farid, you owe me a super chat. Can you help me with my goal? Farid? Since you are ready to pay, can you help me with a super chat? I need a pickle tickle. I don't know what that means. Religious views. I like ice cold. I like water with ice in it. But I don't have an ice maker. So at home I just do cold water, but I like when it has ice. Hi, Adam. What do you mean? Can we get 100 likes? Hello, Eric. You guys are being a little crazy tonight. What is up with that? Okay. Hi, David. Oh, God. All right. Let me, work on the stream settings. Thank you, Regina. What is my accent? Well, I have lived in multiple places. That's my accent. Pretty much. Do I not have a... I'll do that one. I should make a dark energy thumbnail. I need to make a dark energy thumbnail. Hi, Toon. Thank you, Regina. You were prob a up down at the start, but now what does that mean? Relativity. Well, I talked about dark energies, so there is that. Good morning to Africa. Hello, Malawi, Africa. Thank you. Please like and subscribe, Africa. I need you. Hello, the one. Do you guys think I'll be able to pay my taxes? I'm worried about it. It's my first year where I have this issue, and I hope never again. I'm scared. I'm scared.